thanks for coming here. So can you hear me? Okay, I think it's good. So I'm going to talk about this this construction of recent work that gives an improvement for independent source extractors. So okay, so as usual, I start with the motivation for this whole extractor problem. That comes from the gap between the very useful, extremely useful randomness computation, for example, used in designing algorithms, cryptography, and distributed computing problems, and the fact that the real-world random source is actually biased, almost always biased, and these typical applications will require this random bits to be uniform. And also in cryptography, another reason to study this problem is that even if you have original uniform random bits, for example, use the secret keys, that secret key can be compromised by an adversary. For example, if the adversary uses some side channel attacks to gain some partial information about these kind of secret keys. So all of the above just suggests that it's important to study the problem of how to use imperfect randomness in these typical computations. And to model imperfect randomness, by far the standard model is called weak random source, which is the most general model. So basically, we model the random source as some random variable, or in other words, a distribution over some n-bit strings. And we measure the entropy of the source by the standard concept of min-entropy, which says if the source has min-entropy k, then that means for any particular string in the support of the random variable, the probability of taking that string is at most 2 to the minus k. And for most applications, you actually can think of the source to be what we call a flat source, which is basically just a uniform distribution over some large subset. For example, a large subset that has size at least 2 to the k. So that's the definition for weak random source. And then what is a randomness extractor? So basically, that's the ideal case where you would hope that you have a deterministic algorithm such that whenever you are given a weak random source on the left with some kind of entropy, and you hope that you can extract output a distribution on the right that is almost uniform. And we measure the error of the distribution to the uniform distribution by the statistical distance, which is basically the L1 distance between these two distributions divided by 2. Okay, so that's our goal. But then it's easily shown that if you just want to design one such deterministic algorithm for every source, if you want it to work for every weak random source, then this task is actually impossible, even if the entropy of the source is as large as n-1, and even if you just want to output one single bit that is some constant close to uniform. So this is not hard to show, but then the thing is that given this negative result, so actually the study of extractors has therefore been pursuing 2 kind of directions. So the first direction is called a seeded extractor, where the extractor is given another independent, truly uniform random bits at the seed. And generally, the length of the seed is required to be much smaller than the length of the output. Let's say something like order log n bits. And then if you have this help of the additional random seed, then indeed it becomes possible to extract random bits from the original source. And in fact, we can do pretty well in this case. We can extract almost all the entropy of the source with a small statistical error. So there has been a bunch of works related to this construction of seeded extractors, starting from this paper by Nissan and Zuckerman, and then those more recent constructions, which can so currently we can achieve almost optimal protocols for this kind of extractors. Sure. Yeah, it's actually 1 minus alpha for any arbitrary constant alpha.
So you can make it epsilon and then still have the same
Oh, you mean the epsilon in the error?
in the m, right? And still
Yeah.
have the same kind of thing.
No. I mean, it won't be log in the. If you put m times 1 minus alpha, it won't be log over there.
No, the M and Lange and they can get 1 minus little 1. Okay?
Yeah.
Little or 1, but it's still not like log.
What's that dependent on that? You want 1 minus
For seed length log n, you get k minus k over polylog k. Yeah. For any polylog.
Okay. So anyway, so it's pretty close to optimal, and one important property we need to this extractor have is this so-called strong extractors. So in other words, we want the output of the extractor to be close to uniform, even if you condition on the seed that is given to the extractor. And actually, most of the constructions of the seed extractors are indeed strong extractors, because otherwise it's not so meaningful. So, by the way, so the strong extractor, this property is kind of important to use in this talk for the independent source extractors. I'll explain later. So there's another direction for extractors is to construct seedless extractors for sources with some kind of special structures. And so far there has been these.
Seedless is without the epsilon.
Right. So without the truly uniform random bits, as in the seed extractor case. So these are some kind of sources that have been studied. First case is called algebraic sources, which means the source has some kind of algebraic structure. For example, like bit fixing sources, affine sources, polynomial sources. So each one is generated in the previous case. And then second case is where you have multiple sources that are kind of independent of each other. So this one is what I'm going to talk about today. And there are also sources that are based on complexity theory. For example, sources that can be sampled efficiently. For example, sources that are generated by SA0 circuits, and sources that are generated by small space computations like branching programs. But for this talk, I'm going to focus on the second case of class of sources. Okay, so let's talk about independent source extractors. So the extractors are given a multiple of independent weak random sources as the inputs. And then the extractor is supposed to output a distribution that is close to uniform. And so here, if you have L independent sources, then this extractor is called L source extractor. And so we're trying to extract from sources with length n, and each one has min-entropy k here. So if we wonder what kind of parameters can we get from these extractors, then as we have shown before, it's not possible to extract from one source. Then how about two sources? So actually, you can show that if non-explicitly, so actually extractors do exist for just two independent sources, even if their entropy is as small as something like log n plus order 1. And actually, even more, what you can show is that most of if you take this function to be a random function, then actually most of these random functions are very good two-source extractors. So that's these kind of parameters are what we're trying to achieve for independent source extractors. And in another view, if you view as the extractor as a graph, then this is actually also related to Ramsey graphs. So for example, if you have two extractors for two sources, then each source you can view it as coming from like n equals 2 to the m minus strings, where you view it as a bipartite graph, where each side has big n number of vertices. And then for any two vertices on left and right, there is an edge between them. And then if you consider the output, one single bit of the output of the two-source extractor, if it's 1, then you color the edge to be blue. If it's 0, then you color it to be red. And basically what the extractor says is that whenever you have a bipartite clique of size bk equals 2 to the k, then this clique cannot be monochromatic. So it has to contain both blue edges and red edges in this clique.
Exactly, will contain them with roughly the same number.
Right. So this shows, so if you view the extractor's graph, then it's also related to this kind of Ramsey graphs. Sorry?
Ramsey graphs is related to dispersors, not to extractors.
Yeah, because that's a strong case, but you're right. It's actually related to dispersors, but I'm not going to just define dispersors. But in short, it's just a relaxation of extractors. And also, these kind of independent source extractors also have two applications in distributed computing with imperfect randomness. They also have applications in cryptography with imperfect randomness. Okay. They also relate to other kind of extractors and other pseudo-random objects. But if we want to go into explicit constructions, then you might just find that it seems very difficult to construct extractor that achieve optimal parameters. And that's actually true for many other kind of pseudo-random objects. So it's kind of easy to show the existence of such objects, but it's kind of hard to construct explicitly to achieve optimal parameters. And so this table shows some of the previous constructions of independent source extractors, starting from this paper by Carr and Goldrick, where they give two-source extractor. And this two-source extractor is actually pretty well known that if the entropy of the source is bigger than n/2, and then so there's actually like 20 years left before this paper by Barakin, Pagliasso, and Wiggerson, who used techniques from additive combinatorics to give an extractor that works for any linear entropy that uses poly 1/delta number of independent sources. And this was later also improved by this paper by Barak, Kindler, Chateau, and Sudcombe, Wiggerson, who reduces the number of sources needed to 3, but still only works for linear entropy. So Raz in this paper further improved in some sense of the two-source extractor and three-source extractor, whereas his construction only requires one of the sources to have, let's say, entropy greater than n/2 or linear entropy, and the other two sources can have like logarithm entropy. And it has this two-source extractor and three-source extractor. And so this construction due to Bourgain is the current state of art for two-source extractors. So it works for entropy slightly below half, something like 0.49 n. That's two-source extractors. And in the general case, if you want to extract from sources with entropy k, then this paper by Rao and Barak, Rao, Chateau, and Wiggerson actually gives an extractor that uses all the log n over log k sources. So the special case, if this k is polynomially small in n, then these extractors takes a constant number of sources. And there's also a recent paper by myself who, in that paper, I give the three-source extractor, which works for entropy slightly below square root of n, like n to the half plus an arbitrary small constant delta. So these are some constructions of previous extractors. And
How many bits do those outputs say out?
how many bits
Yes.
of the output? So
Roughly the input. Well, it depends on which one.
right, most of them like output at least a linear fraction of the being entropy here.
Yeah, also Bourgain.
But BIW,
That's also, yeah.
Any other questions? Okay. So in this new work, so first, I would give an extractor that for general NK sources that uses only or the logarithm of log n over log k plus another constant number of sources. So this actually, in this case, improved the previous best result exponentially. And also this kind of extractor, like the BRSW extractor, can also be applied in somewhat weaker settings where the sources are block sources instead of truly independent sources. And as I said before, these kind of extractors can have applications in distributed computing with weak random sources. Even if for entropy as small as something like polylogarithm in the length of the source. And by using this new extractor, so actually give this synchronous Byzantine agreement protocol. So it's just some distributing problem, which even if the entropy, even if the weak source has entropy as small as polylog n, it can tolerate roughly 1/5 of the 40 players. And just to note, in the optimal case, even if you have truly uniform random bits, the optimum is like 1/3 of the.
This was not doable with the previous multiple source.
Right.
So getting log n instead of log n.
Yeah, it's crucial. I kind of explained it. And also in this leader election problem, it also improves results. It gets a protocol that tolerates roughly 1/4 of the 40 players, and optimal even with true randomness is like a half. So these are pretty close to the optimal results. And like I said before, the previous result, if you just use the previous independent source extractors, what you can do is that you can, for this kind of entropy is 2 to the log n to some constant delta. What you can do is you can tolerate it like 1/3 plus 1/delta fraction of the 40 players. And that's actually pretty small if this delta is a small constant. So this improvement is actually crucial for these kind of applications.
When you say that the optimal is, say, 1/3, you mean that we know that this is optimal, or just that there is an upper bound?
We know it's optimal because if the 40 players exceeds 1/3, then it's not possible to achieve.
Yes, I mean a question of random extraction. It's just not possible.
Right.
Yeah, I understand. What I'm asking is whether we know that 1/3 is achievable, or maybe 1/5 is there.
No, 1/3 is achievable.
1/3 is achievable.
Yeah, if you don't have, if you have as much randomness, you don't.
Oh,
For these applications, having the best extractor will give you also the best protocol?
Sorry?
For these applications, if you had a random extractor, like the best extractor, with optimal parameters, would it give you also the best protocol?
So like if you have a 2-source extractor, then actually I think the simple application will get something like 1/4 here instead of 1/3. So it's still not clear even if you have the best extractors, it's still not clear how to achieve 1/3. 1/3 is achieved by using truly uniform random bits. And so now I'm going to go into some techniques, and I'm going to focus on the construction of this independent source extractors. So the applications in distributed computing is just a simple application of the extractor, so I'm not going to discuss in this talk. Okay. So to show the construction, I'm going to first introduce something that is called a somewhere random source. So basically, you can imagine that it's a matrix that has n rows and m columns. So it's actually a random matrix. So it's called a somewhere random because at least one of the row of the matrix is uniform. And how to obtain such a somewhere random source? So suppose you have a weak random source, and then what you can do is that you can take a strong seeded extractor. even if you do not have the seeds, what you can do is that you can try all the possible values of the seeds. And because the seed length is generally like all the log n, then what you get is you get a big N equals poly n number of rows, such that at least one of the rows is close to uniform. So in this case, you get something that is close to being a somewhere random source.
So we can assume we have such a
Yeah. And so previously, the extractor actually in this paper by Rao and Barak, Rao, Chateau, and Wingerson works by actually constructing this kind of condenser for somewhere random sources. And the condenser works by reducing the number of the rows in the somewhere random source each time while consuming another constant number of independent sources. Like in one step, it reduces the number of rows in the somewhere random source to some smaller number. But once the number of rows in this somewhere random source gets small enough, it's kind of easy to extract randomness from such a source, and maybe plus another constant number of independent sources.
But sorry, what was the connection between this NK source and the somewhere random source? So how are you doing this mapping?
Yeah, you take a strong seed extractor that you already have with seed length order log n, and you try all the possible values for the seed, which is 2 to the d equals to poly log n. For each seed, you get a row of this source on the right.
It's just another way of describing seeded extractors. The extractors without randomness that produce a polynomial number of strings, one of which is random.
Okay, sure.
Yeah.
Almost all of them are.
So yeah, in fact, almost all of them are. And that's actually important for the improvement of the extractor. Okay, so the condenser for, let's further discuss this condenser for somewhere random source.
Wait, but does anything in that view have to do with multiple source extractions, or that's purely
Not
the
yet,
seeded?
not
Not yet, okay.
Yeah, that's just
That's
one source.
Each one can give you this thing.
So the condenser in this paper by Rao and Barak, Rao, Chateau, and Wingerson, so in each step, roughly decreases the number of rows from, let's say, big N to something like N over K to the 0.9, where K is the entropy of the weak source. And so you can say that and each time it also uses another additional constant number of random sources. So you can see by this relation, it roughly uses order log N over log K, number of independent sources. And this is kind of limited by the techniques in this construction of these condensers. So what we do in this new construction is that we give a new condenser that in each step can decrease the number of rows from roughly n to something like n to the 3/4. So you can see that if this n is much bigger than k, let's say for example k is polylogarithm in n, then actually in this case it's decreasing n from n to n over n to the 1/4, and n to the 1/4 is much bigger than k to the 0.9. In this case, this condenser decreases the number of rows much faster than the previous condenser.
And this can work even if the entropy is logarithm, polylogarithm.
Yeah. It can work for actually any kind of entropy as long as it's polylogarithm. And so
How many sources does it use?
in this step, you just use one additional random independent source. And then finally, when the number of rows in this source reduces to, let's say, something like k to the 6, then we can use at that point we can use the extractor in the PRSW paper to extract from such a some random source plus additional constant number of random sources. And so that gives so if you do the calculations, then you can show that so this extractor uses something like all the log n over log k plus order 1 number of sources. So that's a high-level idea of the extractor. And then I'm going to describe the construction of the condenser. And to do that, I first show that there is a connection between this problem and the leader election problem that I mentioned before, but I haven't defined what is the leader election problem. So let's say you have a some random source on the left that has n rows and m columns. So in fact, there is let's say a linear fraction of the rows that are close to uniform. So what you can imagine is that you can associate each row of this source to with a player pi. So you can imagine there are m players on the right. And what is the leader election problem? The leader election problem is, suppose you have a bunch of players, and some fractions are non-list, and the other players are corrupted. So the goal of the leader election is that you want to design a protocol to select a player from these m players, such that the property that the selected player is the honest player is at least some positive constant. So that's a leader election problem. And what is the connection between these two problems? So you can view that the random rows in the left sum random sources, you can think of it as the player associated with these kind of random rows are the honest players, because they have uniform random bits. And the other rows, they could be not uniform, and they could also depend arbitrarily on the random rows. And you can think of them as faulty players.
The random rows can also depend on each other, right?
Yeah, that's right.
Also, even the uniform can depend on each other.
Yeah, that's what I asked.
Yeah, and you're right. That's also some thing that I'm going to discuss later. So so the random rows are associated with honest players, and the other rows are associated with faulty players. And then so on the left-hand side, we want to reduce the number of rows, while we want to still keep the source to be a sum random source. So that's equivalent to saying that on the right, we want to select a small committee of the players where we have enough number of honest players in this small committee. So that's the kind of equivalent between these two kind of problems. And then, so if you think of the leader election problem, then there is already a protocol for this kind of committee selection problem. And this is simple but also elegant problem due to fake, called the lightest beam protocol in this paper. So what does the lightest beam protocol do? So again, let's assume you have m players and some constant fraction are honest. And now the honest players, let's assume in this case that the honest players have uniform random bits that are also independent of each other. Yeah. So what the protocol does is that first you take some number of bins, let's say b bins, and then each player uses his random bits to randomly select one bin. And in this step, what the faulty players do is that the faulty players can actually wait first to see the honest players' choices before they make their choices. And that's why the faulty players' choices can depend arbitrarily on the honest players. Back in the sum random source, that's equivalent to saying that the bad rows, the bits in the bad rows can depend arbitrarily on the bits of the uniform rows. And then finally, once you have done all of these bin selection protocols, you will have the players who select the lightest bin to form the selected committee.
Then it doesn't matter.
Right, that doesn't matter.
But what if all the honest players choose the same bin?
But they are choosing randomly. That's the beautiful
That's the
idea
point.
there. Is that
But they are but they are the
in the
randomness
case of
depends on one
independent.
another.
No. In the case of the Friday story is in the case of independent. So the beautiful idea is that the independent good ones will choose randomly, so they'll be roughly half-half.
Yeah.
And then the bad guys, if they want to have a
Just fill up
majority,
the
they'll
line.
choose
If leader independent, I understand.
So that's actually the idea of the next slide. Okay, so that's an illustration of the lightest beam protocol.
By the way, so for these types of protocols, you only need bounded independence, right?
Yeah, that's right. That's exactly
So,
what
I mean,
we
you
came
only
to the.
need, like, even K, I mean,
the
not
number
even,
of pins.
yeah.
Yeah, that's also something I'm going to talk later. So you are faster than this. Okay, let's say this is illustration. So let's say the blue balls are let's say they are the honest players. So the honest players first make their choices like this. So this like throwing balls into bins. And then the red ones are the 40 players. Then after the honest players make their choices, the 40 players make their choices. So like this. So eventually, after all these players have made their choices, the lightest bin is selected, and these players form the next committee here. Okay. And exactly like you guys have been said before, the key observation is that if you assume that the honest players, their random bits are independent, then by using a Chernoff kind type argument, you can argue that with high probability, the honest players are distributed roughly evenly into each of these bins. And therefore, no matter if this happens, and no matter what the 40 players do, the lightest bin has to contain roughly the same kind of fraction of honest players as in the original protocol, as in the original set of players. Because if the 40 players want to put more 40 players into this bin, then that bin wouldn't be a lightest bin in this protocol. And if you do the computation, then assuming that the random bits of the players are indeed independent, then roughly in one step you can decrease the number of rows from n to something like log n. And that's pretty good, but let's get back to the condenser problem. So again, as I said before, it's easy to get this summer random source. And actually, I already said that most of the rows are close to uniform. So that's good for us. But the problem is that, in fact, it's kind of impossible to make that all of the good rows to be independent and uniform. Right? It's simply because you don't have so much entropy in this kind of weak random sources. But the observation and the solution is that it's enough to use like bounded independence, for example, pairwise independence, in order to run the lattice bin protocol. In this case, you can use, like, for example, in the case of pairwise independence, you can argue the property by using like Chebyshev's inequality. And you do the computation, you can show that in each step you can roughly decrease the number of rows from n to, let's say, n to the 3/4. Okay, and so now the problem is that how can we get such a summer random source that the rows are kind of, let's say, pairwise independence. And for yeah, that's right. But it's not equivalent to saying that the pairwise independence. Yeah, that's not enough. I don't think that's enough, right? Right. So and then to get this random source, I have to describe another connection to another type of city extractors called non-malleable extractors. So this is a so we have seen these strong city extractors before, which says that the output of the extractor is close to uniform conditional seed. And this non-malleable extractor says that to strengthen this, that the output of extractor is close to uniform not only given the seed, but also given the output of the extractor on another seed that is different, but otherwise arbitrarily correlated to the other seed. So this is indeed a strengthening.
You should say it slowly. I think it's not trivial definition.
Yeah, okay. So right, so first you have a random seed y here, and then let's think of this a as an adversary. So this adversary picks another seed, ay, which is different than y, but otherwise can be arbitrarily correlated to y. So we want the output of the extractor to be close to uniform condition on the seed y as well as the output of the extractor on this correlated seed ay here. Okay. Any questions about this definition? Sure.
So a question about something on the last slide. So when you said you use pairwise independence to go from n down to the 3/4, like if you had used, say, log n-wise independence, you had better load guarantees, right? But then you would use more random bits. Is that something was that a bottleneck you were trying to avoid, or is that not that important for you?
It would be better if you could achieve for logarithmic
Yeah.
independence. Then it will you get to
You get the log star, not
Right.
log log.
It's probably hard.
it's better to get larger independence in that in the construction, because you can reduce the number of rows faster in that way.
Okay, so I guess there's something, I mean,
It's even pairwise independence. It's hard
He
to
hasn't shown us
generate.
how to do pairwise independence.
No, pairwise is just
But it's
collision property.
so, but it's non-trivial to get such kind of somewhere random sources that have this bounded independence in their rows.
okay, what else is
Okay, so, and as you can see, I have to go through all of these things to get only pairwise independence in this somewhere random source. So, okay, so this is a non-malleable extractor, and the statement is that indeed, if we have such a non-malleable extractor and you apply this non-malleable extractor instead of the city extractor to get a somewhere random source, then I claim that the somewhere random sources that is obtained is exactly what we want. Because it's from the definition, as long as this seed y gives a uniform random output on this, it's going to be close to your uniform condition on any different seed here.
So what would the definition of non-malleable extractor look like in order to get higher order bounded independence?
Yeah, that would include more of the.
Then you have so it's several tests, and then still it has to be independent.
Right.
You will get the output on several other seeds that are correlated with the seed.
But they're not adversarial recorders somehow. That's the only thing that can probably help us.
Sorry.
I mean, in this definition, do you really need it to be true for all?
You're right. You don't need it to be true for all the seeds, because you only need independence in the uniform random rows in this.
On average.
Yeah.
On average, exactly.
On the other hand, non-malleable extractors don't exist for small min-entropy surveys, so you have to do something when you use them.
Right. So this is some other stuff's going there. Yeah. You have a question?
So you're using this only for the good seeds, for the seeds that give you a uniform distribution?
Yeah.
So you could potentially replace the definition with the UM on the right side, but conditioning on. So if AY is a good, if both Y and AY are kind of good seeds for X, then this is close to just a uniform string.
But still, you have to ensure that they are kind of pairwise independent. But this definition is slightly stronger than what we're going to need. Yeah, but you have a question?
The m less than k over 2 restriction follows from the first line, right?
The m over m less than over 2. M less than k over 2 is just because of you want to have enough entropy in this.
I mean, it follows from the first line.
Yeah,
It's
it
not.
follows.
yeah,
Yeah, it's
right.
not a restriction. It
Yeah.
just wouldn't work otherwise.
Yeah, but then unfortunately, the best known non-malleable extractors only works for entropy 0.49, and this is a recent construction of myself. So that's bad for us, because we want it to work for k as small as polylogarithm again. So then fortunately we can turn to something a relaxation of the non-malleable extractor called non-malleable condenser. You can forget about all these parameters. Just the intuition is that the non-malleable condenser says conditioned on the output of the different seed. This original output is close to having some kind of entropy instead of mean uniform. So that's the idea of the non-malleable condenser. And
And the one, it means that it contains only one bit.
no, this is L. Sorry.
Oh, and
Yeah. So, and fortunately, we have this non-malleable condenser for arbitrary entropy. This is also a recent construction of myself. So we can try to use these kind of non-malleable condensers instead of non-malleable extractors. Sure.
Just the quantification that for all mappings A, it holds it for 1 minus epsilon factor of y, blah, blah, blah.
Right. Okay, so now I'm going to kind of describe a variant of the non-malleable condenser constructions in this paper, and to show how we can get from this to how we can use this to build some random sources that have this pairwise independent property. So the next few slides are going to be a little more technical here. So to do that, I first describe this protocol called alternating extraction. So suppose you have a source X on the right, and you have a source Q on the X on the left and Q on the right. And on the right, you also have let's say a small uniform random string S1. So what the alternating extraction protocol does is that, so imagine these are two parties. So first, so the right-hand side sends S1 to the left, and the left-hand side uses an extractor to an S1 the seed to output R1, extracting from this source X. And then he sends his R1 back to the right and uses this R1 and the seed to extract from this Q to get another uniform seed S2. And then you send S2 back to the left again. You compute R2, which is an extractor applied to X and S2. And you keep on doing this for some kind of T steps. So you get a bunch of random variables R1, R2 through RT here. By the way, all of these, as long as the size of these R's and S are small, you can show that all of these R's and S are close to uniform. And let's assume that the size of each R and each S is some parameter S here. Okay. So the nice thing about this protocol is that now suppose you run this protocol with this source X and another source Q prime and S1 prime there. So this Q prime and S1 prime, they could be arbitrarily correlated to the previous Q and S1. But the important thing is that, so here X is going to be independent of all of these Q, S1, the joint distribution of Q, S1, Q prime, S1 prime. So if this happens, then what you can show is that, so if you look at any particular step I here, then as long as the size of all of these Ri's and Si's are small, then what you can show is that if you condition on all of these Q primes and these are I primes before the I step, and then the Ri's in the previous slides from I plus 1 to RT, they're still close to uniform, condition on all of these previous random variables. So any questions about this kind of protocol? So, so intuition is mainly because the size of these Ri's and S's are small. So each step you're going to extract fresh random bits from the remaining entropies of the sources X and Q.
So you just need that R times T is less than the entropy on X.
Yeah, right. Okay, and then I'm going to introduce something that is called a look-ahead MAC. So this kind of thing is used in these security protocols, and particularly is introduced in this paper by Dodos and Weeks.
They also introduced non-malleable extractor.
Yeah. So suppose you pick a uniform random seed Y here. And then you can view this Y as a Q and S1. So Q you can just view it as Y. And S1 is just a small slice of the source Y, which is also uniform. And then you do this alternating extraction between X and Y. You get a bunch of these R's.
Where do we get the S1 to be uniform? Where do we take this from?
S1 is just
the whole Y is uniform.
Yeah, because the whole Y is uniform. So you do this alternating extraction protocol, you get a bunch of these R's. And this T is 4 times D for some. So D is typically the length of a seed extractor. So now what you can do is you can define a mapping from the strings of length D into the subsets of these elements from 1 through 4D. And the mapping is actually done by each bit. So for each bit, you're going to take 2 elements in this through 1 to 4D. And if this bit is 1, you're going to take 4i minus 3 plus 1 and 4i minus 1. If it's 0, then you're going to take 4i minus 3 and 4i. So just as a simple case, think of the case where you have just 1 bit, 0 and 1. If it's 0, then you're going to take the 2 elements 1 and 4. If it's 1, you're going to take the two elements 2 and 3. So the nice thing about this mapping is that whenever you have two different strings of length d, so as long as they're different, there is some index between 1 and 4d such that so this HU greater than or equal to j just means the set of the elements in this set H which are greater than or equal to j. So this says that whenever these two strings are different, there's an index j such that the size of the set in this HU that are greater than or equal to j is bigger than the size of the set in HV that is greater than or equal to j. So as a simple case, you can think of it just 1 bit. If it's 0, 1, so in the 0 case, it's 1, 4. In the 1 case, it's 2, 3. So if you use 0, you can take the j to be 4. And because the HU has a 4, then HV doesn't have anything greater than or equal to 4. If it's 1, then you can take this j to be 2. And HV has 2, 3, which are bigger than 2. And HU just have a 1, 4, which is bigger than 2. So that's the kind of a...
All these subsets are of size exactly a half.
Yeah, that's right.
They're organized so that you always have...
Yeah.
You can pick a point from which one is greater than another.
Right.
For any
Yeah. So anyway, this is a simple construction, but it's just you just need a little bit of manipulations to find out that this is indeed true here. So what you do is that once you get this bunch of R's and you get a string U, so the Mac is just you take these Ri's where I is are the index that are in this set HU here. Right. So for each string you first use this map to get set HU there. And so this R is obtained from this alternating extraction protocol. And you just take these Ri's with the index I in that subset.
It's a way to distribute to many players sets of keys somehow.
Yeah, somehow.
With this property, with this bullet, use this representation.
Yeah. So it's kind of ensure that whenever these two strings are different, yeah, I'll explain in the next slide.
And we should think of T is about log n.
T is log n because T is sure.
What is H sub u?
H sub u is just a mapping from F FU here.
It's a subset of the R.
Yeah. Sure.
Would it be helpful for quantitative, parameters if HU greater than J was much larger than HU greater than J? Or does it matter?
It doesn't matter much actually. So as long as it is bigger than that by at least 1, that should be enough for the applications. Right. Any other questions? So okay, describe these. So now I describe the variant of this non-malleable condenser. So first you pick a seed Y with order log n number of bits here. And then you pick two independent sources, x1 and x2 here. So first thing you do is that you use the source x1 and the random string y to output another string w here that is close to uniform. And then you use this w and with the other independent source x2 to do this alternating extraction protocol to get these R's, R1 through RT, where T is equal to 4D, and D is order log n bits. The output of this variant of this non-malleable condenser is just using this look-ahead MAC, using this R as the key, and using this Y as the string of the information here.
So
Mac is affirmative.
A family of sets, right? You didn't say where the d-bit string is coming from. So for every, so this
Yeah.
capital V is all the image of this.
Yeah,
All the subsets coming from this.
right. Yeah. Right. So basically, it's a function of x1, x2, and y. Here. And y is usually the seed.
Yeah, but I'm saying when you say output, this V is really a family of subsets of the Ris.
Yeah. Right.
Yeah, all these possible outputs.
Right.
Of this.
So why is this non-malleable intuitively?
No,
Because
it's not.
Yeah, I'm going to explain in this slide. So to show that it's non-malleable, you first imagine you pick another different seed y prime that is different than y. Then, as I said before, because these two strings are different, then there is an index j here, such that the subset of hy greater than or equal to j, the size is bigger than the size of hy prime greater than or equal to j. Here. So now you let RH to be the concatenation of all the Ris, where I is in this subset H1, Hy greater than or equal to j, and you define RH prime likewise. So before I have mentioned that in the alternating expression protocol, this Is, whenever this I is greater than or equal to j, is going to be uniform condition on all these I primes with I less than j. That's by the property of the alternating extraction protocol. Yeah. So which means this RH is also uniform condition on the fixing of all these I primes with I less than j. And then just notice that the size of this RH is at least s bigger than the size of the string IH prime. This is because we have this condition here. And because RH is uniform. So that means if you condition on the further fixing of RH prime, then this RH still has entropy, roughly entropy S. Condition on both of these fixings. And you notice that the fixing of both of these two determines this string V prime. This means that V has entropy S, roughly S condition on the fixing of V prime. Questions about this? Okay, good.
So the same proof should work just to show the same to show that also V prime has S min-entropy more than beta, right?
No,
But
because
I mean conditional.
right.
If you it's symmetric. The
Yeah.
argument is symmetric. If you take V prime, it will have
Yeah.
bits of entropy, even conditional.
Yeah. As long as the seed y and y prime are both good, so yeah. So it's like this, and then but we only get like pairwise close to having some kind of entropy instead of pairwise independence, and then so we need the next step to obtain in the somewhere random source. So what we do is that first notice that the output of the non-malleable condenser has size something like 2D times S. So what you can do is you can take this S to be bigger than 2D. Then in that case, you also have this this S is bigger than the square root of M here. So this means that the entropy in this output of the non-malleable condenser is bigger than the square root of the length of the output.
So it's not enough to have pairwise, conditional entropy?
No, because you want to write the lightest beam.
How do you select the beam? I mean,
Yeah.
most of the bits are, it's a very limited distribution. It does not give you a random beam. It will give you maybe a random subset. You'll always fall in a small subset of the beam. And it's not you want to pick a beam at random, but you don't have a random number. You have something very little.
Yeah. So, but anyway, we're going to try the seed for every seed for the condenser, and we get this n times m source, which is
Can you go slower?
yeah.
So the output of this condenser is
Yeah, you can.
What was the parameter that came out of the original somewhere random source, right? Could be linear.
M is 2D times S, actually, in the output of the non-Malleable condenser. And yeah, you just take S to be bigger than 2D. So then you can make sure that S is bigger than. So anyway, we're going to try every seed for the non-Malleable condenser, and then we obtain this source, which is like pairwise having entropy condition on the other. So what we do now is that so you can prepare a constant number of independent copies of such kind of sources. And then for each row, because each row has this entropy bigger than square root of output length, so you can apply this extractor in this BRSW paper, which uses only a constant number of sources to extract the random bits from this kind of sources. And because so these are you just prepare a constant of independent copies. So because in each copy, almost all the rows are like good. So in this constant number of copies, like almost all the rows are always good, aligned in this somewhere random source. And then after you applying this extractor, you get this somewhere random source, which have this kind of pairwise independent property.
So what is the upshot of this? You can take any number of, any constant number of independent sources, arbitrary, right? And generate from them another constant number of somewhere, maybe fewer, of somewhere random sources. And each of these has this pairwise independent property.
So one somewhere random source which has this pairwise independent. So along with the
you need just one, right? Sorry.
Yeah.
Just one.
We need just one.
Just one. Right. So where are you taking the independent sources from? One you need for the construction of the condenser.
All right. Actually, we need from all of these independent copies, because if you consider just one row, then once you apply the extractor, the output is close to uniform. And then you condition on the fixing of these rows, and then the other rows, if you pick another row, so the independent copies in this row still has entropy condition on fixing of the previous rows.
So can you say, just summarizing this slide, how many independent sources you take in order to construct this?
A constant number of independent sources, because you use a constant number of sources to prepare this source, and you use another constant independent copies. So that's also a constant.
This from here, this W, I understand, but for the bullet before, you need how many sources do you need for the condenser you use?
Like actually two.
The two, you
Yeah.
just use two for
Yeah.
the exchange, right? That's
Yeah,
all it is.
two. Right. And then this is also constant. So we're almost done, except there's a small issue here, which is the error. So we have to control the error in the applications. So, so actually in the somewhere random source, each pair is the good pairs growth is something like epsilon close to uniform. So for some epsilon equals to 1 over poly n. But that turns out to be not enough for the application because this epsilon is kind of bigger than 1 over n. And so actually, if you do the computation, you want to analyze the lattice beam protocol, you want this epsilon to be actually kind of be smaller than 1 over n squared. And then what?
multiplicative, like you just need a collision probability guarantee.
Right.
You can't even guarantee that.
If the epsilon is bigger than this,
Might
then
just miss one band, right? Still.
because you have a large like error. When this error is too big, then it's kind of hard to ensure that.
No, I understand that you can't get it directly from this error bound, but can you look at the analysis and do it directly?
What do you mean? You mean?
Like just found the probability that two things get mapped to the same value.
Yeah, that's because when you do this, you have to consider the uniform bits are just only epsilon close to uniform. They're not truly uniform. So anyway, we need to somehow reduce the error, but we can't. A simple way to do that is that, again, we prepare a constant number of these independent copies. Then for each row, we just take the XOR of the copies. And so the error reduces to something like epsilon to the C.
You do it in parallel.
Yeah.
So you may reduce the number of good ones.
Yeah, but that's okay because it's just a the error fraction, the fraction of the bad rows only gets multiplied by some constant C.
You want to keep the number of good players higher than half throughout this.
It doesn't have to be half, just have to be some constant linear fraction. So it's a little different than leader election. In that case, you need it to be greater than half. But here, you only need it to be a constant.
So you do just simplification.
Yeah, because in the final somewhere random source, you only need one row to be like somewhere random in order to apply the, let's say, the BRSW extractor. So, but anyway, you use another constant copies, and so that's also a constant. Okay, so right. So the actual condenser is that first you use a constant number of sources to prepare the somewhere random source, and then in each step you use the bits in the rows to perform the lattice beam protocol. But then at the end of the lattice beam protocol, you have to take another fresh random source X and a strong seeded extractor. And you use the strings in the lattice beam of the C's to extract fresh randomness from X. And the outputs of the extractor now will form a new somewhere random source for the next step for the lattice beam protocol. So this is just to ensure that the bits in the next lattice beam protocol are fresh random bits independent of the previous.
And also are longer. Because here you are about logarithmic. I mean, here
Yeah.
You shrunk to a calculation.
That's right. Yeah.
So you do it not just for particular fresh X, but all the X's subsequently used.
Yeah. And by the way, these somewhere random sources will also keep the structure of the pairwise independent, as long as the output is not too large. Let's say less than k/2, something like that.
For the lattice beam protocol, let's say you have pairwise independence.
Uh-huh.
The row has it's not truly random, but has entropy 1 minus epsilon.
Has entropy 1 minus epsilon.
So can you still run the lattice beam protocol? I mean, how bad will it be?
I mean, once you have a bin which is not occupied by the good players, then you're in trouble, right?
Right, I guess you have to ensure that the
Well, it depends on the function. If you can hit only 99% of the beams, then the balance would be affected, but maybe not too bad.
Right, that's good point. Maybe you don't go 10 to the 3/4, but go to n to the 1 minus epsilon and still maybe. Because then you won't have to do this. You can work with condensing.
right, but then I don't think, yeah. Yeah, that's a good suggestion. Maybe we can work it out later. And so here's a final diagram of the whole extractor. So first of all, you use a constant number of sources. So you get this somewhere random source with pairwise independent property. And then you run the lattice beam protocol to reduce the number of rows in the source. And then you use one additional weak random source to get another somewhere random source by applying this seeded extractor. And then you repeat the lattice beam protocols again until the number of rows in some random sources gets down to say k to the 6. So this step uses something like all the log n over log k number of sources. So finally, you apply this the extractor in this BRSW paper plus another constant number of sources, and then that's where you get a distribution that is close to uniform. So in total, this extractor uses all the log n over log k plus all the 1 number of sources.
So one more question. If you want to do this, let's say maybe not for log, but even just log, do you still need to use the non-malleable extractor stuff?
What here?
Yeah, I mean, let's say in the lattice beam
Uh-huh.
Does it become any simpler? Like, because even that construction is not really
Yeah, actually, I'm not sure about that. Yeah. So you want to?
I'm asking maybe if you even if you want to do the earlier result, does it you still need the non-malleable extractor and stuff?
Yeah, I don't know the answer. I have to work it out. Yeah. Okay. So finally, some future directions. First, you want to get better extractors. For example, use higher orders of independence. You want to achieve small error. So right now the error is something like 1 over poly k. So it might be good to achieve exponentially small error here. So actually, we already have some progress in both of these directions. So the final direction is to try to generalize this technique and then apply to, for example, dispersers and maybe extractors for any other kind of sources. And that will be all. Thanks.